Well, in addition to reflection that we just studied in the law of reflection, another very important idea of waves is refraction. And I want to explain it and define it here for us. And it's true in general. So regardless of whether it's a two-dimensional or three-dimensional wave. So, and that can even be represented as a single dimension with rays. So refraction, what is it? It's just the bending of light. And it results from the fact that the speeds change in a medium, or the medium itself changes. When the medium changes, it's a different speed. Remember, the speed of a wave in a medium is based on the medium alone. So if something about the medium changes, the speed changes. The illustration I like to start with is if you're driving a car down the road and say your right tire hits the soft shoulder, that's a different speed of medium. It's a slower medium. Now take your hands off the steering wheel. What happens? You guessed it. The tires are drawn into the ditch because the right side is slowing down while the left side stays going fast, and you careen into the ditch. So that's kind of an analogy to what happens here. So we have a fast medium, and here's the crests of the waves coming in. And now it's entering this is not a barrier. This is a transition. This here is a transition into a slower medium. So it's not bouncing off. Like light through glass is a good illustration of that. Or water coming along here, deep water, and all of a sudden it's shallow water. Actually, the speed of waves changes in the shallow water. So it's slowing down, and it causes a bending. You know, the part that hits it first slows down, and it literally causes this change in direction of the front as it passes through. So we have the wavelength of the fast medium, which is just crest to crest. Remember, these are crest lines. And so the distance between crests is the wavelength. So we have the fast wavelength and the slow wavelength. Now you know that since they were produced originally by something, the time to go from one crest to the other in both cases is the same. They both take the same amount of time. So, and they're both a wavelength in their own respective mediums. Therefore, the velocity is proportional to the spacing. The bigger the spacing, the faster it's going. If the spacing doubles, the speed doubles. If it gets cut in half, the speed is cut in half, etc. So now we know the speed is proportional to the distance between crests. I mean, yes, that's right. So, because the time is the same. Now, let's kind of reverse it here just to make sure we're understanding this. We have our slow medium, and we're going to go transition into a fast medium. Well, now it bends the other way. Kind of bends, you know, in this case, outward or leftward-ish. Forward, I don't know. It's kind of hard to say that in words, but you can see here what's going on. So, in fact, the spacing is increasing here. So the law of refraction. We got our fast medium and our slow medium. And so I'm showing these two fronts, and kind of in an expanded view, and we're going to do a little bit of math on this. Yep, a little bit of math as we investigate the wavelength here and this wavelength and the various angles and come up with the law of refraction. That's going to carry with us into our next unit when we study light. So the distance between the crests is the wavelength, and that's just the speed of the crest times the time. So Vt. So lambda 1, so this is lambda 1, the space across here, is V1, the speed of medium 1, the speed of a wave in medium 1 times the time. And here's an angle theta 1. Okay, don't worry about, well, you'll see how that relates to the other side in a second. So I just wanted to say, I was going to say that if we take a normal, this is not showing the angle of incidence or refraction per se. It's just theta 1. So I didn't want you to get confused with that. Theta 2, or I'm sorry, lambda 2 is the distance. That's V2 times t, the speed of the slower medium times time. Okay? And here's theta 2. Now, we have two triangles in this thing that have a common hypotenuse. Has a common hypotenuse. And there it is. So this is the common hypotenuse for this triangle and for this triangle. Both right triangles. So now we can put them in a ratio. And this is going to be our law of refraction, which is that the sine of theta 1 over sine of theta 2. Okay, the sine of theta 1 gives this. Now it's opposite over hypotenuse. Sine of theta 2 is opposite over hypotenuse. Okay, and so that ratio is really the sine of theta 1, lambda 1 over sine of theta 2, lambda 2. And that's the ratio. That ratio is v1t over v2t. Of course, the t's go away, so it's v1 over v2. And we have a special name for that, the ratio of the velocities of the medium, or the wavelengths of the medium. That ratio is n. So this is the law of refraction, and is called the index of refraction. N is the index of refraction. It's equal to that ratio. Okay, I want to illustrate the that index of refraction just one more time, just with a little bit different picture here. The rays of the same wavefront are perpendicular to the front itself. So the rays are perpendicular to the front. The normal is perpendicular to that transition region we showed. So those two perpendiculars kind of cancel out in a sense. It follows that the angles can be drawn in a different way. They can be drawn like this. So we have our normal, and we're going to have a ray coming in. There it is. Now theta 1 is actually the angle of incidence. And then, all right, so basically, with respect to the normal, theta 2 likewise is shown as such. And if we take those two angles, the ratio of the sines of those, you get the same result that we did before. So it's equal to the ratio of the wavelengths, which is the ratio of the velocities, and that is the index of refraction. Okay, so that's another way to think about it, probably a little bit simpler. Now, dispersion, another idea, and simply, well, it's not necessarily so simple, but the idea is, in detail how it works is not the really important part, but when refracted, different frequencies, and different frequencies have different wavelengths, will have slightly different indices of refraction. So the index of refraction of a given wave in a certain situation is not necessarily set in concrete, so to speak. It depends on the wavelength itself. So it's a new idea. So we have refraction. And so here we have a fast and slow medium again. We're going to show a wavefront coming in. There it is. So we got the ray of incidence and the refracted rate angle as well. Now this is low frequency, meaning a large wavelength, right? So here's a large wavelength, which is corresponding to a low frequency, and we see this particular index of refraction, namely the ratios of the sines. Now a higher frequency is going to have a smaller wavelength. So it's the same scenario, same set of mediums, but it's a higher vibration rate. So this front, you'll see them spaced closer together. And that just means that the time between the crests is less. And when this happens, you'll notice the refraction illustrated here is going to be different. So we have our angle of incidence and refraction. But in this case, at least, as the wavelength goes down, the wave is bent less. Look how this one is bent more than this one. If you do that ratio, you get actually a different index of refraction based on the different wavelengths. So that's a reality of nature. It also explains why rainbows form. But when we study light, we'll find out some details of this actually change. Nevertheless, that's the basic idea that is required to separate colors in a spectrum from the sun, which is what's manifested in the rainbow.